We will now talk about domain walls and domain wall width. And basically we're dealing with the boundary between two domains. And there are two possibilities in terms of the energy of the configuration for these boundaries. It can be either infinitesimally small, or it can have a transition between the domains. So we will talk about what energy terms derive these two limits. So there are two possibilities regarding the boundaries between domains either the domain boundary is infinitesimal in width. So this means that, as you can see here, you have neighboring moments at the boundary belonging to one domain or the other. So meaning that the nearest neighbor moments belong to one domain or the other. And what is the problem for this configuration? As you can see, we have a ferromagnetic ordering within a domain, so J is positive. But if you look at the exchange energy that is in between the two moments that are nearest neighbors in two different regions of the wall, this is going to be maximized. So this is going to have a cost in terms of exchange energy. Now, if you want to minimize this exchange energy, the second possibility would be to have a gradual change of angle between the moments so that we will have less exchange energy. So the second possibility is the existence of a transition region between these domains. Okay. So what is deriving this type of a configuration? Well, we have an easy axis. So let's say the easy axis is as shown here. It's the y-axis. So the anisotropy energy minimization requirement basically drives this type of a configuration. On the other hand, this is going to cost exchange energy. So let's recall here that this is causing anisotropy. So we can say that the anisotropy energy is happy. However, exchange is unhappy. So this is good for anisotropy. Now, the other scenario where I have a transition between the two boundaries. This is going to make exchange energy happy. But anisotropy energy is increasing, so anisotropy energy will not be too happy with this type of a transition between the two boundaries, because we have deviation from the easy axis throughout the wall. Okay, so as we found out, the anisotropy tends to make domain walls thinner, since the anisotropy energy is lowest when all moments are aligned along easy axis. They are pointing along easy axis. On the other hand, the exchange energy tends to make the walls thicker since the exchange energy is minimized when neighboring moments are parallel. Okay, so let's try to find this equilibrium configuration of the domain wall width. So as you can see, I call this delta the distance between two domains, the domain wall thickness, and phi is the angle each neighboring moment is making with respect to the previous one. And this is a hypothetical 180 degrees domain wall, and you can see here my easy axis are along y-axis here. So easy axis is the y-axis. So you can see that the two domains have their magnetic moments pointing along the y-axis. So if I write the exchange energy, it is a minus mu zero, a magnetic moment m interacting with the exchange field H exchange. And H exchange I can write as gamma times saturation magnetization in the PHYS mean field approximation. And this is going to be equal to gamma times number of atoms per volume multiplied by magnetic moment per atom at 0 Kelvin. So this is what we know. Then we can write the exchange energy between neighboring moments as minus mu zero gamma times n mi dot mj, where we're basically looking at the energy per moment. So this is energy per moment, because I'm not summing over all the moments. And here I have m sub I and m sub j are neighboring moments. Okay. So according to three-dimensional classical statistical physics, the thermal energy per moment is going to be equal to the average value of 1/2 kx square plus ky square plus kz square plus 1/2 vx square plus vy square plus vz square. This is because they are belonging to a lattice and they're oscillating about their equilibrium positions in 3 dimensions, and each quadratic term gives a half a kT contribution. So by equipartition theorem, I find that the exchange energy is 3 Boltzmann constant times temperature. So there's a contribution half a kT times 3 and half a kT times 3 here from each quadratic term. That is at the Curie temperature. So this is going to be equal to mu 0 gamma n m squared. That is the energy per moment. Or I could write this as mu 0 z j m squared using the nearest neighbor approximation. So j is the nearest neighbor exchange constant, and z is the coordination number. So this relationship basically gives me for Tc mu 0 gamma and m square over 3 times Boltzmann constant, or mu 0 z j m squared divided by 3 times Boltzmann constant. Okay, and for iron, we talked about, for example, Tc is 1043 Kelvin, exchange energy is 4.3 10 to minus 20 joules and 5 times 10 to minus 21 joules per pair of moments in this case. Okay, so using the nearest neighbor approximation now, I can write this exchange energy as minus mu 0 z j mi dot mj, where I'm considering the nearest neighbor interactions. There are z of them for this moment, and this is going to be equal to, if I call the angle between the moments as phi, minus mu 0 z j m squared cosine phi. And for small angle variation, for small phi, cosine phi, for phi approximately 0, it's small, can be written as 1 minus phi squared over 2 using our Taylor series expansion. Now I'm going to consider a linear chain. Now if I have a linear chain case, so you would have, if you look at each of these moments, they would have only 2 neighbors, neighbor 1, neighbor 2. So on a linear chain I have only 2 neighbors. So I can say that z will be equal to 2. So the exchange energy would be mu 0 j m squared. So for z I substitute 2 m squared. For cosine phi I substitute 1 minus phi squared over 2. I had the minus sign here, so this has become a plus and minus like this. And this is going to be equal to, the 2's will cancel, so I will have mu 0 j m squared phi squared minus 2. And if I have n lattice parameters in the domain wall, so I look at the number of pairs. I have 1, 2 pairs, and each have a distance of a lattice parameter in between. So if I call n the number of pairs of moments, then I have a, the lattice constant, for a 180-degree domain wall. The angle phi between each moment, each pair of moments, will be pi divided by n, and the domain wall width will be equal to n times a. Okay, so for example, here n is equal to 3, domain wall width is equal to 3a in this example. Okay, so with that, I want to write the total exchange energy, over n moments. So this is for n moment pairs. I have mu 0 j m squared. As usual, we can set our energy scale starting from minus mu 0 j m squared times 2. So I only look at the angular dependence here. So this is going to be then, with my new definition of energy scale, mu 0 j m squared phi squared multiplied with n, because I have n pairs. So if I look at the exchange energy per area, total exchange energy per area, that is a squared. So if I have a lattice constant a, the area of one side of a cell is a squared. This will be equal to mu 0 j m squared. So for phi, I'm substituting pi over n, pi squared n over n pi squared over n squared, so phi is pi over n, multiplied with a squared. So you can see that the n's will cancel here, and I will find that the exchange energy per area of the wall will be given by mu 0 j m squared pi squared divided by n a squared, which I'm going to call exchange stiffness A times pi squared over n a. I'm going to define this exchange stiffness now. So this is the exchange energy per area of the wall. Okay, so this A, I call the domain wall and exchange energy per length. So A, I define as exchange stiffness and it is equal to mu 0 j m squared, the exchange energy per length. So that is the definition of exchange stiffness, which has some temperature dependence because the J, the coupling constant, will decrease with increasing temperature. So this is in joules per meter, it's energy per unit length. So if you look at the value for iron, for example, exchange stiffness is 1.75 10 to minus 11 joules per meter. This is at room temperature. Now I want to write the anisotropy energy, the other side of the story. So here I have talked about exchange. So this part was about exchange picture. And here I want to talk about the anisotropy picture. So I'm assuming a uniaxial anisotropy. So, okay, let's assume uniaxial anisotropy with anisotropy constant K1. So if I write the anisotropy energy per area, this will be equal to K1 anisotropy energy per volume multiplied with N times A. So this will be equal to, therefore, K1, the first approximation, anisotropy constant times delta. This is in joules per meter square. It's energy density, areal density. Okay, so this is basically it. So for this one, I have the anisotropy constant, that is energy per volume, multiplied with the thickness of the wall, gives me anisotropy energy per area of the wall. If I have basically the full change in the basically I'm considering the angle to change from easy axis to hard axis here. Okay, so let's talk about the total energy of the wall, domain wall energy. And for this one, I'm going to call this domain wall energy sigma. Sigma will be equal to the anisotropy energy per area of the wall, which is K1 times the domain wall width. And then I have the exchange energy per area of the wall is exchange stiffness pi square over an A. So it is A pi squared divided by delta, the width of the domain wall. And at equilibrium, we should have this energy minimized. So d sigma, d delta should be equal to 0. So if I take this derivative, I obtain K1 minus A pi squared over delta squared is equal to 0. So this is going to give me K1 is equal to A pi squared over delta squared, or the domain wall width to be pi square root A over K. So the equilibrium domain wall width will be pi square root exchange stiffness divided by the anisotropy constant K1. And if I substitute this result into the domain wall energy, then sigma will be equal to K1 pi square root A over K1 plus A pi squared multiplied with 1 over pi square root K1 over A. So you can see that the first term here will be pi square root AK. The second term will be also pi square root AK, so AK1. So therefore I find that domain wall energy will be equal to 2 pi square root AK. So this is my domain wall energy. This is measured in joules per meter squared, and this is my domain wall width. Okay, so if we look at, for example, 180 degrees domain wall in iron, It has an anisotropy constant K1, 4.8 times 10 to 4 joules per meter cube at room temperature. The lattice constant is about 2.5 angstroms. The magnetic moment per atom is about 2.14 Bohr magnetons. The exchange energy per unit length or we can say the exchange energy is 1.9 times 10 to minus 21 joules, and we obtain a domain wall width of 395 angstroms, which is 160 lattice parameters. Roughly 160 lattice parameters. So if we look at different magnetic materials, iron, cobalt, and nickel, our favorite elemental ferromagnets, we have for iron, magnetic moment per atom at 0 Kelvin, 2.22, cobalt 1.72, nickel 0.62. Saturation magnetization, as you can see, it decreases from 0 Kelvin to 300 Kelvin. There's a slight decrease for iron, cobalt, and nickel. Exchange energy, so somehow this is missing here. So let me write down. This is 4.5 10 to minus 21 for cobalt. So 2.5 10 to minus 21, 4.5 10 to minus 21, and 3.2 10 to minus 21 joules. Curie temperature 770, 1131, 358. Anisotropy energy constants, as you can see here. And if you look at the anisotropy constants at 300 Kelvin, you can see that we have the highest anisotropy in cobalt here. Lattice spacing are similar. Domain wall thickness, so all of these parameters determine the domain wall thickness. So in iron, it's about 138. So as you can see, this all depends on the temperature, and different sources will give different numbers. So these are rough calculations. And the domain wall energy per area, so the energy per area in joules per meter square, is changing like this from iron to cobalt and nickel. So all of these numbers come from the reference, the book of David Giles, Magnetism and Magnetic Materials, and the references therein. Okay, so we talked about domain walls and domain wall width. The domain wall width, that boundary between the two regions, domains, whose orientations are determined by the anisotropy in the sample, is determined by a competition between two energies, exchange and anisotropy. The exchange energy basically derives a transition, a finite width domain wall width. The anisotropy energy derives a sudden change in magnetic moment going through a domain wall. So it is the best scenario for anisotropy is to have a zero width of the domain wall. And we calculated the exchange energy for a linear chain of magnetic moments for n moment pairs, and we found that it can be written as exchange stiffness energy per unit length times pi squared over domain wall width. And anisotropy energy, assuming uniaxial anisotropy, can be written as anisotropy energy constant, the first constant K1, anisotropy constant K1, which is in the energy in joules per meter cube, multiplied with the length of the wall, and A, that gives us anisotropy energy per area. And the total domain wall energy is minimized with respect to the domain wall width, and we find that the domain wall width is pi square root A over K1 for a 180-degree domain wall, and domain wall energy per area is 2 pi square root AK. So you can explicitly see as the exchange stiffness increases, domain wall width increases. As anisotropy increases, domain wall width decreases. So we have typical numbers for iron here, and here is a more comprehensive list of magnetic properties of iron, cobalt,